The purpose of this video is to start with the second order differential equation and derive the fourth order differential equation, which has some drawbacks, but it has a lot of advantages. The idea behind this derivation is quite simple. So let us begin with the second order differential equation and simply differentiate it. Then we can see that on the right-hand side, m prime could be replaced with v. If we differentiate one more time, we can replace v prime with q, and this way we end up with the fourth order differential equation, and that's the differential equation of interest in this video. And the key advantage of this differential equation is that we can simply look at the load without constructing the bending moment diagrams. Of course, the key disadvantage of this differential equation is that it involves higher order derivatives, and therefore it involves 4 rather than 2 constants. So we have to work a little bit harder on the math. Boundary conditions. Since we have 4 constants, we need to figure out how to write more boundary conditions. To this end, we simply say that the physical boundary conditions could be imposed on the deflection itself, the angle, bending moment, and the shear force. So these are the physical quantities that I can assess by looking at the problem statement. Of course, I can replace theta with v prime, m with ei v double prime, and v with minus ei v triple prime. And this way I can rewrite the boundary conditions using v, its first derivative, second derivative, and third derivative. And these are the mathematical conditions because they involve only the function and the derivatives of v. When I write down boundary conditions, it is critically important to follow the rule that there are only 2 boundary conditions per endpoint. 2 and only 2. It cannot be 1 or 3 or 4. It must be 2. Let us look at a very basic example problem to which we will apply the fourth order equation. So, of course, the differential equation is very simple. Our Q is constant because it's a uniformly distributed load. And now let's talk about the boundary conditions. At x equal to 0, we have a roller or a pin. It doesn't matter. The important thing is that the displacement is equal to 0 because it's a pin, and also the moment is equal to 0 because the rotation at the support is not constrained. Now I can replace m with the second derivative and conclude that at x equal to 0, v is equal to 0, and v double prime is equal to 0. These are physical boundary conditions, these are the mathematical boundary conditions, and they're exactly 2 at x equal to 0. Now, if I look at the other end, x equal to L, I simply claim that the 2 ends are essentially the same. V equal to 0, m equal to 0 translates into v equal to 0 and v double prime equal to 0. So here I have 4 boundary conditions, right? Of course, the 2 lines look the same, but of course one of them is evaluated at x equal to 0 and another at x equal to L. How we solve it? not particularly complicated. All I have to do is I start with the differential equation, and then I tediously integrate line by line. So the third derivative, qx plus c1. Now to get the second derivative, I integrate this line, right? So c1x plus c2, and I integrate once again. This time I integrate this equation, and finally I obtain the relationship that tells me what is V. It involves the known term proportional to the applied load, and it involves four integration constants, C1, C2, C3, and C4. To find this constant, we proceed with evaluating the boundary conditions. So let us see how it works. We take the expression for V, evaluate it at 0. So that's the expression for V. I substitute x equal to 0, and it's very easy to see that everything except for C4 is equal to 0. So the first boundary condition implies that C4 equals to 0. V double prime of 0 equal to 0. That's the expression for V double prime. I evaluate it at x equal to 0. Implies that C2 is equal to 0. Now the algebra gets a little bit more complicated, but not by much. V of L, that's the expression for V, evaluated at x equal to L. That's what I get, and this whole thing is equal to 0. And finally, V double prime of L equal to 0. The expression for the second derivative is evaluated at x equal to L, and I obtain this equation. So I have four equations, 1, 2, 3, and 4. Now we can solve them. So these are my four equations, rewritten and slightly simplified, right? And so all I have to do now is to solve for the constants, and these are the constants that I obtain. And now I can just simply go back and reconstruct, using these constants, the entire deflection. V is given by this expression, so you could see it's a polynomial of degree 4, which is reasonable. If you differentiate it 4 times and multiply by EI, you will obtain exactly Q, which is what we expect from the differential equation to begin with. We could also calculate the interesting displacement at L equal to 2 or in the midpoint, and we get this expression which tells us what is the deflection. Okay. Now, in principle, we are done here, but I would like to exploit this expression further than just calculating what is the displacement in the middle. To this end, I observe that actually it packs everything we need to know about this beam. Let me pursue this. Let's talk about the slope. If I start with the deflection curve, I can differentiate it and I get the equation for the slope. I observe that if I substitute x equal to L over 2 into this expression, I will obtain that V prime of L over 2 is equal to 0. Perhaps it's not that complicated to notice if you just simply use symmetry arguments. But this also tells us that V has a critical point because V prime is equal to 0 at L over 2, and therefore V is the maximum value. Somewhat trivial result, but nevertheless, it just shows that we can confirm our intuition. Now let us see how the deflection line can be used to calculate the bending moment. So we start with the equation for the deflection line and then simply use the relationship that connects the bending moment to the second derivative of v, which gives us this expression for the bending moment. It's actually very easy to see that this equation is nothing but the bending moment diagram. So we can also check that at x equal to 0 and at x equal to L, m is equal to 0. And of course, if I substitute x equal to L over 2 into this expression, I'll obtain QL squared over 8, which is again easy to infer by constructing the bending moment diagram or making a cut in the middle of the beam. Let us now look at the shear force. Again, here's the equation. Now the shear force is related to the third derivative, and it's given by this expression. If I evaluate it at 0, I get QL over 2, which is the reaction force up. If I evaluate it at L, I get minus QL over 2, which also represents a reaction force up, which is good. At x equal to L over 2, V is equal to 0. It means L over 2 is the critical point for M, and this allows us to claim something that is probably somewhat obvious, but good to confirm, that the bending moment in the middle is maximum.